So yep, thanks for joining us, everybody. For those of you who don't know me, my name's Joseph Guyan. I'm a product manager at ANSA Data Analytics. In case you don't know who we are and what we do, we specialize in the analysis of case haul logging data. And I've been working in the field for about 20 years now. And the last 14 of those spent at ANSA itself. As you know, today we're going to be talking about how the quality checking of production logging data shapes the reliability of the data itself and the answers that the reports provide. Jennifer, my colleague today, she's going to be doing the heavy lifting. She's going to be presenting the bulk of the slides. Maybe Jennifer, you could say a few words about yourself.
Yes, so hello, my name is Jennifer Leyes. I'm a case haul data analyst. I focus on the analysis and interpretation of caliper data, cement evaluation, and production logging. And I am looking forward to discussing the data sets that I brought for you today.
Thank you. So depending on your level of experience in the topic, you might know that there's many possible scenarios that we can talk to in this one. And given the time that we have available, we're not going to be able to cover them all. But what you will get is an introduction, and the introduction will help you perhaps articulate those questions. So next time that you have a PLT data set in front of you that you're processing, or perhaps you're basing decisions off, you'll be able to approach it in a more sort of enlightened manner. As I've already said, we've got the Q&A panel going live throughout the PowerPoint session. We'll have my colleague Jose answering those questions, and we're not going to be having a live session at the end because we've got a decent amount of material to get through. So just to keep it to the right time, if you put your questions and answers, your questions into the chat there, and we'll get to those as we go. And what we can do at the end, if we do miss anything, just feel free to get in touch, or I can check the log as well, and we'll get back to you. So with that, we'll go to the first slide. Just in case, like I say, I don't know exactly your level of experience in the audience here, so what is production logging? And again, this is half an hour on its own, but today it's 30 seconds. So a production log is essentially a set of measurements taken inside a completed well to understand how the fluids are moving. So where they are entering from, where they're leaving, and how they behave in between those points. Now we're going to concentrate on the tools there, the temperature, pressure, and spinner today. Together, they can give us the well profile. And that's a term that describes where the fluids are, where they're moving, and what's happening. So why people need the well profile? So they need that to support their decisions. So operators who would like to identify such behavior as cross-flow, leaks, they can use it to assess previous interventions like water shut-off or acid stimulation. We're not going to be diving too deep into the physics of the measurements today, but really how the sensors respond and what those responses tell us from a quality checking perspective. Next slide, please. So why does it matter? So I guess flippantly, if I was being flippant, I could just say garbage in, garbage out, but we'll treat it with a little bit more seriousness than that. Quality checking impacts both sides of the table in a way. On one side, you have operators. They're basing important decisions. They need confidence in the acquired data. They're paying for answers to specific questions, and good quality checking underpins those answers. If your data quality starts off as poor and perhaps you're not assessing it in the right way, then straightforward optimizations, other intervention decisions, they become slower and less certain, and their confidence in you is reduced. And for those service companies, the quality checking is how you deliver on what you're promising. It helps you catch those issues early, present results that you can stand behind and be proud of, and avoid any unnecessary rework that could come later. So both sides want solid quality checking. It protects value from the operator's side, and it protects credibility from the service company's side. Next slide, please. What we're going to do today, just to give you a bit of a structure, Jennifer is going to start with an overview of each of the core sensors that we've mentioned, talking to them each in isolation. So you can get to see how to identify trustworthy data for each of those tools on their own. Then she's going to cover some real quality checking cases. So you'll get the focus there, I think, is looking at the bigger picture and how all of them line up together. So they've all got to add to the picture, which can give you the answer in the report. And again, just a final reminder about the questions and answering. Just please use the chat or the Q&A panel, and we'll get to as many of those as we can as we go. So with that, I'll hand over to Jennifer.
Okay. So before I show you the data sets I brought today, I just wanted to give you a little bit of an overview of these data sets. So they have been acquired with production logging tools that have been properly maintained and calibrated as per manufacturers' recommendations. The wells that I'm going to be showing today are injection wells. The fluid is a single phase fluid, either water or gas. And the overall survey objective is the determination of the inflow profile. This is calculation of the total injection rate and calculation of the contributions of the different injection zones. With that in mind, I want to say that the assessment that we will do in here for all the measurements will be basically assessing whether this data is of enough good quality and suitable to achieve the survey objectives. With that in mind, I'm going to move to the data set that I want to show you first. So this first data set or set of passes is from a water injection well. The passes were acquired while the well was injecting. The tool stream was conveyed through Wardline, and the data was acquired through SRO mode, which is surface readout. So the first step that I want to highlight for QSwing or to make sure that the data is of good quality is assessing whether we have a correct depth match. So basically, depth match requires you to align the depth of the data sets to a measurement that you know that is at a correct depth. In order for us to do that, what we usually use is the gamma ray curves. So basically, we have the gamma ray curves that we had acquired during the PLT survey, and we made sure that we align it to a reference gamma ray. This reference gamma ray is generally provided by the client, and we know that is properly depth corrected. Additionally, or optionally, if you don't have gamma ray reference or if you don't have a gamma ray sensor in your tool stream, you can use the CCL curve. The CCL curve basically gives you a defined signature at different completion items, like for instance, packers or sliding slips or even the collar connections. So basically with this signature, what you can do is make sure that you correct this to the depth in which those components are meant to be. So these depths are generally provided in the wellbore schematics. So things that we need to look out when we are doing the QC of the depth matching is making sure that both the gamma rays that we are correcting and the gamma rays that we are using as a reference are showing very definitive features in both definitive features that are matching in both the reference and the gamma rays that you have acquired. One useful thing is, for instance, the peak tags, which are radioactive markers that are in the wells, and they are at a definitive depth. So you can use these ones as a correlation. The response of the gamma ray at these peak tags is going to be very definitive. It's going to be like a spike, a very high value. So you can use this as a correlation. For instance, this is one of the options. Additionally, let's say if your gamma ray doesn't show you many features, you can get help with the CCL curve. Also, another thing that you need to make sure is that after you're doing your depth match with your gamma rays, you also cross-check your CCL response and your completion items, making sure that they are at the expected depths. Another thing to look out as well would be making sure that your wellbore schematic that has been provided to you is the most up-to-date. Things like perforations, depths sometimes get added or get updated, and failure to do so, to have the wrong reference, the wrong wellbore schematic as a reference, might lead to the wrong interpretation. With the data set that we have in here in the screen, we can see that, I'm gonna just highlight in here, we can see in here we have some good features that are correlating. Our curve in black is our gamma ray reference, and our other curves in the left are all our gamma rays from our different passes. So we can see that they are correlating okay. They have been dead matched using the gamma ray. And additionally, we can see as well the response of the CCL. We can see clearly the response at Packard. We can see the response of the CCL at one of the SSD, for instance, and we can see that they are aligned properly. So from that point of view, and analyzing the gamma ray and the CCL, we have done our QC for the depth matching, and now we are confident that our data is at the correct depth. So I'm gonna move to the next slide, which will focus in the next curve that we're gonna QC. So that will be the pressure curve. So basically the pressure measurement is a indication or give us the profile or the pressure profile within the wellbore. It also helps us giving us an indication of the wellbore stability. It can help us with the calculation of fluid properties downhole. And also through its derivative, we can determine what type of fluid we are dealing with. In this case, for this data set that I am showing, we can see that for the majority of our passes, the curves are overlaying each other. The exception is the very first pass, where we see that the general profile is similar, however, is a little bit towards the left. So this is perhaps indication that the well at the first pass was still reaching stabilization. However, we can see that as the passes continue to be taken, the curves are looking or are overlaying each other, which is a good indication of the wellbore getting stable. Another thing that we can do with this pressure curve is also calculate via the software. We can calculate the derivative of this curve, and this will give us an indication of the density of the fluid that we are dealing with. In here, we have it here in the right, and we have a curve that is generally steady and is giving us a value of approximately 1 gram per cubic centimeter. So this is indicative of fluid water, which is what we were expecting to see, as is a water injection well. So also we can see that this density is kind of steady throughout the well. The pressure gradient is also steady. And yeah, this is what we were expecting to see in this well as being a water injection. So we can move now confidently to check the next curve. So I'm gonna move to the next one. So that will be. So the next curve that we're gonna look at is the temperature. So it's been highlighted here in green, the box in green. So basically the temperature gives us a profile of the temperature of the system. It also helps us with the calculation of properties of the fluid downhole. It can be used for the determination of the production profile, and also it can give us indication of small fluid entries through its derivative. So in this case, we have a water injection well. So normally the temperature of the injection fluid is generally lower than the temperature of the formation in where we're going to inject these fluids. Because of this lower temperature takes more relevance, or is more definitive, or let's say take more precedence within the temperature of the system. So with that in mind, we are seeing here our temperature or the temperature profile of this well being dominated by the cooler temperature of the fluid being injected. So basically, most of the passes are overlying and are telling us this, that the temperature of the system is being dominated by the temperature of the fluid being injected. If we look at our well schematic, we can see that our bottom SSD is around this depth. The bottom SSD with the bottom packer is around this depth, and that would be the deepest point where we can possibly have injection. And we can see as well with the temperature that around this depth, the temperature is converging to a higher value. This is the temperature of the formation. So what we can say with this temperature profile is that the injection is going all the way down up to around this point in here, up to the lowest point, which is the SSD. And after that, we can see that the temperature is trying to be in equilibrium with the formation temperature. So this is expected for this injection well, and is giving us the response that we are expecting. So we can say that this temperature is of good quality. Similarly, like we saw in the pressure, like the first pass, we saw that the pressure response was towards the left, was a little bit different. We can also spot the same thing in here for our first pressure. That is slightly, it follows kind of the same profile, but it's slightly towards the left. So this is also indicative that the wellbore was still stabilizing during the first pass being taken. So this is correlating with what we saw in the pressure, so is expected in this case. So having said that, I'm gonna move to the next slide. So move to the next slide. So the next slide and the next data that I want to review is the flow meters with the line speed. So basically, the flow meters give you indication of the fluid movement. However, it doesn't give you indication of what type of fluid is being moved. Also, the flow meters help you identify the areas where you are producing from or the areas in where you are injecting to. It helps you identify leaks, and it helps you as well identify and quantify cross flows. So the RPSs, the response of the spinners, which is the RPSs, will be related to the relative velocity of this relative velocity. Basically is the velocity of the fluid minus the velocity of the tool stream, the velocity which you are running in hole or going out of the hole. So in PLT, what we are interested is about the velocity of the fluid, right? So we need to also bear in mind that this RPS's response depends on the fluid and where the spinner is immersed to. And that there is also the friction of the bearings in the spinners, and there is also sometimes variations in the viscosity of the fluid. And this will give like not necessarily a linear response. So because of these effects, we will have to have a calibration that gives us a relationship between the line speed and the RPSs and the apparent velocity of the fluid. So that's why we have to do a spinner's calibration. So this spinner calibration is achieved by doing different passes up out of the hole and going into the hole. And that's why we have in here different passes and different velocities at which we have acquired data. And for us, from the QC point of view, it's important to make sure that these passes are acquired at a steady speed. So that will be our, let's say, our first QC of the line speed, making sure that is as constant or as stable as possible. We are not too interested about the value itself of the velocity, but as long as once we are in certain velocity, that velocity is kept steady. basically what I was saying is that for PLT logging, we require to have a steady velocity or steady logging speeds at our different passes. And in this data set, this is what we are seeing. We are seeing that the line speed is steady, and that gives us confidence as well in the response that we're going to get into from our flow meters. In this case, for this survey, they have two flow meters, IFN and FCS. We can see that we have a continuous response for most of the interval that we have logged in both of the curves, in both of the flow meters. We can see as well that the response is repeatable between the two flow meters. We can see that the response is steady as well. Mostly, we are seeing most steady in the FCS than in the IFM, but we can see as well that even in the IFN, the curve is variating. This variation is still around the same, let's say, consistent value. Okay, I'm gonna go out. So the response of the IFN or an FCS, we can see in here, there is a step change, a reduction of the absolute value of the RPSs, and this is correlating with the location of our SSD. So this is expected. This is likely the point in where the fluid is being injected. So this is expected. We see that there is correlation. This is a good indication. Similarly, in this bottom SSD, we can see as well that there is a change in the RPS's response related to a place of outflow or injection. So this is expected as well. We have from the wellbore schematic that both these SSDs are open, and we can see here an expected response of fluid being injected in there. Additionally, like we said before, based on the temperature curve as well, general analysis of general analysis of data, we said that below this SSD there was a velocity fluid velocity 0. There is no movement. So we can see as well that response here in the bottom for both the flow meters. We can see that the response for the passes up and down is mirroring. So that's a good indication as well. So yeah, well, having analyzed all of the curves, the gamma ray, the CCL, the pressure, the temperature, flow meters, and the line SPD, we can see that overall our data set is of good quality and is good for achieving the survey objectives and moving to the next step, which will be the processing and the quantification and the results for the client. So yes, after this, I'm gonna move to showing you two data QC examples with all the information that we have seen, and we're gonna do our QC assessment of these two data sets. Okay, I'm gonna close in here. Yeah. Okay, so here I have the example of data QC number 1. This was a gas injection. The passes were acquired while the well was being in the injection mode. The tool stream was conveyed through the tractor, and the acquisition mode was SRO mode, surface readout. So looking at the data set that we have in here, we can see our gamma ray is very well matched to the provided reference gamma rate. We don't see any anomalies or high gamma rates that can say that there is any scale in there. We also look at our CCL. We can see that there is a good match to the completion items. For instance, this SSD in here. This is SSD in here in the examples, but if you look through the CCL, you can see that there is a good match in there for all our completion components. We can see as well of our pressure curve. Pressure curves for all the passes are generally showing the same profile. The profile is repeatable. There is, however, certain separation between the passes that is related to perhaps the well still achieving stabilization. However, for now, we can consider that the well is stable enough for the survey objectives that we want to achieve. Similarly, we have the temperature. We have all the passes being shown here. They are showing a general similar profile. There is a slight separation as well between the temperatures of different passes. We can see a slight event, temperature event in here, perhaps later on for when we are writing our findings for our report, that will give us a talking point for the interpretation. But we can see that it also correlates with some events in the flow meters. We have in this data set, we have a density tool as well. And we can see that the density tool is showing us a constant value. It's around 0.4 grams per cubic centimeter. And is showing us a steady value, which is what we were expecting to see. This is a gas injection well, only one phase fluid involved. So it's very important to see that this is constant and is steady. So that's good, it's as expected. Now we have in here our flow meters and our line speed. So talking first the line speed, we can see that there are 3 passes going down and 2 passes going up. The velocities in Excel are steady. They are good. However, we can see that there is a kind of a short spacing or short separation between the velocities. Sometimes this is related to the operational restrictions because you are doing the logging with tractors, so you might not be able to have a lot of flexibility or a lot of flexibility with the velocities that you can log in or log out. So that will be one point to note in here. And then we have in here our flow meters, which looking at them overall, we see that we have a continuous response throughout the log interval. The response is repeatable between the 2 flow meters. Another point to see is when we see changes in the value, in the RPS's value, these changes are correlating with the depths in where we have our sliding sleeve devices. So we are making sure that our responses in the flow meters, whenever we see a change in the RPS, this change is related to let's say a predictable or unexpected place where we are seeing injection. So in this case, we're seeing responses at our SSD, which is expected. All the responses, we can verify that these responses are actually taking places taking place in places where we are expecting them to see. In this case, all these changes in RPSs are happening at the expected depths of the SSD. So that's a good thing to see and is overall good. So this data, looking at it, looking at all of it, we are getting the responses as expected. The data is stable, is repeatable, and there are features which are correlatable between curves. It's giving us confidence. However, thinking ahead for the next step and thinking that we want to achieve the survey objectives, the only thing that I will highlight perhaps in here is the response of the RPSs, that you can see that for different passes, sometimes the response doesn't show a lot of separation between themselves. And this is also expected because our separation between the line speed is very short. So that might or might not have a impact within the calibration. So having said that, one of the best practices that our clients or operators do is generally have a separated or dedicated passes just for the calibration. In some cases, what they do is they go higher up in the well where they don't need to use the tractor, so then they can use the conveyance by gravity. They have more flexibility with the velocities that they can log in or log out, and then they can acquire the specific calibration passes. Then we can get the calibration out of those passes and apply it as we will do for our standard logging or injection survey in this case. So yes, so this is the data QC number 1. And I want to move to the data QC number 2. Okay, so this is for a water injection well. The status of the well where we were acquiring these passes were injection mode. I think I kept some, yeah, injection mode, and the tool string was conveyed through coil tubing, and the data was acquired through memory mode. So here in the left, we can see our gamma ray curve. We can see that is very well matched to the reference gamma ray, which is in black. This is a good sign. On good QC, we can see our CCL. Our CCL is quite noisy. Perhaps not very, in this case, not very useful for us to correlate data. However, we have a good match with our gamma ray, so we are confident that our data is depth match properly. We have our pressure curves from our different passes, and we can see that they generally repeat in profile. However, there is a separation between them. It's a noticeable separation. We can see, and perhaps this is indicative that the well is still stabilizing while we are taking this survey. Similarly, we look at our temperature curve, and we can see that the general profile repeats. However, if you look at the top of the log, you can see that the temperatures of the different passes are still increasing while the passes are being taken, or in relation to each of the passes, up and down. So that's indication as well, similar to what the pressure said, that well probably is still stabilizing. We can see as well below this point that, below this point that the temperatures are returning to a value, most likely the geothermal temperature in here. And yes, this is a talking point that we can use later for our interpretation. Okay, so now looking to our velocity or line speed, we can see we have a good spread of line speed. Our line speed is steady, is good. We're happy with it. However, we can see one of the responses of our flow meters, the CFG, is totally clogged, so we cannot use it. The response is absent, so we cannot use that one. We don't have response in there. And we have some sort of response from the ILS. As you can see in here, we don't have response from all the passes. We have from one of the passes for the top half of the log, and we have response from another of the passes from the bottom half of the log, and it's intermittent response for both of them. So basically in this data set, we have, let's say, our QC assessment is that we don't have repeatability, we don't have continuity of the data. So it's gonna be difficult for us to, with the data that we are being provided, it's difficult for us to achieve the survey objectives. So that will be the conclusion from this data QC. However, having said that, there are things that we can qualitatively say from the data set. For instance, let's say we are not going to be able to do a calibration because, as I said before, we need several passes and several responses for drawing a proper calibration. So perhaps what you can do is check another survey or another status survey within another status. Let's say they did a shut-in survey for this campaign, and you can get, maybe check the data and maybe see if you can get a calibration from that well status survey in shut-in, and maybe you can use that calibration for this survey to calculate the total injection rate. Obviously, there is going to be a lot of uncertainties, and these uncertainties will have to be communicated to your client. Also, another option, if you don't have the shut-in survey, could be to perhaps you could use a theoretical calibration from the manufacturers and also calculate your total flow rate. And obviously, there will be a lot of uncertainties involved in this, but these are things that will and have to be communicated to the client. Qualitatively as well, you could say perhaps that looking at your temperature, that your injection went all the way down up to this point, which is the second last slotted joint. This is just from a qualitative point of view. And there are other conclusions that you can perhaps qualitatively say from this incomplete pass that we have in here in blue. Having said that, I think the quality of this data is not sufficient for us to achieve the survey objectives, and it will have to be communicated to the client to take possible arrangements for future surveys or same surveys or future campaigns. And yeah, that's all I have for today. I will go back to Joseph.
Okie dokie. Let's get on to the last slide. So thanks, Jennifer, for working your way through that. I guess we started at the basics there. So you need to understand the well, the survey objectives, because everything hangs off that context. And from there, we looked at the sensors individually. So now we have a good idea of what good looks like for each of those sensor types: pressure, temperature, spinner, and line speed. After that, you started to look at the whole picture, so cross-checking their behavior against each other to start building the confidence in what story you're being told by the data that you have. Once you know that what you have is trustworthy, you're moving on to thinking about your customer, building confidence in the results and meeting the survey objectives. So hopefully, let's have a quick look at the Q&A. I think Jose is taking care of everybody. There's a few questions there, so thanks for those questions. If you do have anything else that comes after the survey, after the webinar today, just feel free to get in touch. So yeah, we really appreciate everybody attending today. With that, I wish you all to have a great day. Thanks very much.
Thank you. Bye-bye.